Good afternoon. I'm Norman Wildberger at the University of New South Wales, and today is the second lecture on this course in the history of mathematics. We're following John Stilwell's lovely book, Mathematics and Its History, and this chapter today on Greek geometry corresponds to his chapter 2. So when we look at the ancient Greeks, we really see a remarkable period of innovation and creativity in human history. So they excelled in so many things, in art, in drama, in philosophy, but probably their most lasting contribution was their contribution to mathematics. And their contribution to mathematics was profound and very important, and still affects a lot of the direction of modern mathematics and modern teaching of mathematics. Today we're going to have a look at that subject in their mathematics, which they loved the most, okay, which was most important to them. That was the geometry. They thought of geometry as sort of being the central subject in mathematics. And they left us one overwhelmingly important book, which was written by Euclid, and it's called The Elements. Euclid's Elements. Okay, and Euclid was around 300 BC. It's hard these days to understand and appreciate how important this book has been in the history of mathematics and in the history of civilization. Aside from the major religious texts like the Bible and the Quran and so on, this is almost certainly the most important book ever written. Okay, its influence was dramatic upon well, Arab civilization, and then Western mathematics was built on it. So for 2,000 years after Euclid's Elements, if you studied mathematics, very likely you were studying geometry using Euclid's Elements as a text. Okay. That situation maintained itself until the beginning of the 19th century, when Euclid started to weaken and then people started to think about alternatives. Okay. But in the 18th century, 19th century, 17th century, studying mathematics at university meant going through Euclid's propositions one by one and learning them all. That was what mathematics was. It's fascinating to think that the direction of mathematics has changed so much that nowadays students in high schools often learn very little geometry. Perhaps you people have learnt very little geometry. Right. So this will be a chance for you to learn some interesting geometry. I have here a lovely book, one of my prized possessions, and it's a copy of Euclid, which was printed in 1723. Okay. It says, printed for Thomas Woodward at the Half Moon, over against St. Dunstan's Church in Fleet Street, and then 1723. And I want to read to you the first 2 pages of this. Okay, it's a preface by Dr. Keel, perhaps the one who put it together. So this is a voice talking to us from 300 years in the past. Okay. A young mathematician may be surprised to see the old, obsolete Elements of Euclid appear afresh in print. And that too after so many new elements of geometry as have been lately published, especially since those who gave us the elements of geometry in a new manner would have us believe they have detected a great many faults in Euclid. These acute philosophers pretend to have discovered that Euclid's definitions are not perspicuous enough, that his demonstrations are scarcely evident, that his whole elements are ill-disposed, and that they have found out innumerable falsities in them, which had lain hid to their times. But by their leave, I make bold to affirm that they carp at Euclid undeservedly, for his definitions are distinct and clear, as being taken from first principles, and are most easy and simple conceptions. And his demonstrations elegant, perspicuous, and concise, carrying with them such evidence and so much strength of reason that I am easily induced to believe the obscurity often attributed to Euclid is rather to be attributed to their own perplexed ideas than to the demonstrations themselves. And however same may find fault with the disposition and order of his elements, yet notwithstanding I do not find any method in all the writings of this kind more proper and easy for learners than that of Euclid. That was 300 years ago. So you see there was already quite a lot of history in Euclid. It had already been around for a long time. There had already been a lot of discussion about its pros and cons. All right, so let's turn to Euclid, and how does he start? Okay, well, Euclid starts off with definitions. And admittedly, these definitions are maybe not so clear to us today. They might not pass muster today. So his first definition is that of a point. What is a point? A point is that which hath no parts or magnitude. What does he mean? Well, he means that a point is something like this, but it's really small. It doesn't actually have a concrete size. Second definition, a line is length without breadth. In this edition of Euclid, a line referred to just a sort of continuous line, a curve, what we would say today. The ends or bounds of a line are points. So as far as he was concerned, when you drew a line, there was a starting point and a stopping point. Any line had ends. And there's many other definitions, okay, involving circles, figures, semicircles, rhombuses, and so on and so forth. And then in this edition, there are 3 postulates. So these are what? That, first of all, a right line may be drawn from any one point to another. So if you have any point and any other point, you can draw a right line joining them. Right line is his meaning of straight line. Okay? So you can draw a straight line between any 2 points. Okay, we'll accept that. Second postulate is that a right line may be continued directly forwards. So if you have a line and you need to extend it, you can do so. You can continue the line in either direction. So the first one is between 2 points there is a line or a straight line, and second is a line can be continued. These days we tend to think of lines as being infinite in extent, but in Euclid's days a line was something that you drew on a piece of paper and it had a start and a stop, but he allowed himself to continue it by maybe making the paper larger. And the third postulate is that a circle may be described about any center with any distance. It means that if you have any center and you have any distance, you're allowed to draw a circle centered at that point with that radius. Okay? So those are the things that he allows himself to do. They are kind of things that he's going to be doing quite a lot. So a circle with given center and radius. Okay, and then there are some other things. There are, in this thing, things called axioms. And the axioms, well, there are 12 axioms. I'm not going to read them all, but there are things like things equal to one and the same thing are equal to one another. What do you suppose that means? Things that are equal to one another, and things equal to one and the same thing are equal to one another. That's right. If A is equal to B and B is equal to C, or if A and B are both equal to C, perhaps we could say. So with axioms such as if A is equal to B and A equals C, then B equals C. So these are kind of logical axioms. Okay, and then there's they're all relatively short until we get down to the 12th one. The 12th one is not short, and it played a major role in the history of mathematics. So here's his final axiom. And sometimes in some other editions this is not the 12th axiom, but rather the 5th postulate. Okay, so the 12th axiom, or sometimes the 5th postulate, depending on what edition we're talking about. If a right line falling upon two other right lines makes the inward angles on the same side thereof both together less than two right angles. So, if we have two lines, two straight lines, which fall upon another straight line, and if these two angles here are on the same side are less than two right angles. What's a right angle? A right angle is like this. Okay, that's a right angle. And what's two right angles? Well, it's sort of like all the way around, what we call 180 degrees. So he's saying that if this angle and this angle together are less than 180 degrees, then the two right lines indefinitely produced will meet each other on that side where the angles are less than right ones. Means that in this case, what will happen if, in our notation, if alpha plus beta is less than two right angles, I won't say 180 degrees because Euclid definitely did not measure angles in terms of degrees. But if alpha plus beta is less than two right angles, then the lines meet. And they meet, moreover, somewhere in that direction. This postulate is also sometimes called the parallel postulate. And it's often stated in a quite different way. It's often stated in this way, that if you have a line and you have a point not on the line, then there's exactly one line through the point which is parallel to the given line. And what does parallel mean? For Euclid, parallel meant that the two lines don't meet. Even if you extend them in this direction or you extend them in this direction, they don't meet. So this was an assumption. This was something that Euclid said, look, this is kind of obvious, so we're going to use this, but we're not going to prove this. And his idea then was to, starting from this framework, to derive all the major results of geometry from first principles using logical reasoning, one step at a time, starting with simple things, building up to bigger and bigger things, each given a clear statement and a proof. Okay, so proposition, proof, proposition, proof, proposition, proof, and it goes on. 13 books altogether, not all of them devoted to geometry, but the first three or first 6 books mostly they're the ones that studied mostly concerned with geometry. Okay, so it would take us quite some time to review all of Euclid's approach, and we're not going to do that. So as it's an alternative. So if you have a look on my YouTube channel, which is NJ Wildberger, I have a series called Math Foundations. And in that series somewhere, I can't actually remember the numbers offhand, in that series there's a series of videos on Euclid that describe roughly what happens in the various books 1 to 13, and give you pictures and so on. So if you want some more detail or perhaps homework, you can have a look at those Math Foundations series. I want to talk about just a few select problems, just to give an indication of what actually a proposition looks like. Okay. So I'm going to choose in book 3, proposition 35. And what does it say? It says that if two right lines in a circle mutually cut each other, the rectangle contained under the segments, which all his nouns are capital, under the segments of the one is equal to the rectangle under the segments of the other. All right, so I'd like to have a look at that theorem. Any of you recognize what it is? It's in a language and a way of thinking that's perhaps a little bit different to our modern day one. But it gives me a chance to explain a little bit about how Euclid thought about things. Now, when we say Euclid, okay, this wasn't all Euclid's work. Euclid clearly took the mathematics that had been developed in the several hundred years before he came along. He synthesized it, he put it together, he organized it in a very clear fashion. It's undoubtedly true that he will have added a lot of his own. He will have thought up some new proofs, but a lot of the material will have been common knowledge amongst the Greek mathematicians of his day. He was writing the first really serious textbook on the subject. Okay, so the ancient Greeks thought about geometry in a quite different way than we do. And it's interesting for us to go back and try to get our heads around how they thought. So to Euclid, a segment like this could not be measured directly. Okay? Euclid did not have a ruler. Well, he most surely had a ruler, but he does not use his ruler in his theoretical development. He does not say, let's measure this line segment, get 17.4 or whatever. Okay. So if he wants to compare line segments, if he wants to say that this line segment is equal to this line segment, and he does say that, what he means is that you could pick this segment up and put it there. Or using the tool of the day, you know, you have sort of a compass. The compass was used to draw circles. So if you get a compass and you open it and you sort of use it as a divider and you get it at that point there, and then you just pick the compass up and move it over there and you put it down here and you see that it's the same, then you say those two segments are equal. That was equality of segments. So Euclid does not measure distance. Does not measure distance. He rather talks about one segment being the same as the other, or he might talk about this segment being twice this one. What does it mean? It means that you can chop this into two, and then you can move that one there, and move that one there, and you can see that this one's twice that one. Or another thing that he might be able to say is that these two segments are in the ratio 5 to 3. That means that you could chop this into 5 pieces and this one into 3 pieces, and each one of these pieces was congruent or equal. Also important to measure, also he does not measure angles. In fact, the whole notion of an angle is quite problematic in Greek geometry, and I'll talk a little bit about that in a while. But let's have a look now at this proposition and try to figure out what does it mean. So it's concerning a circle, and it's concerning two lines that meet the circle. Okay, there's two right lines, straight lines. They mutually cut each other. Here's where they cut each other. And the rectangle contained under the segments of the one. So we've got 4 segments. We've got this segment, we've got this segment, we've got this segment, and we've got this segment. What he's saying is that, let's give these segments some names. Let me call this segment A, and this segment B, and this segment C, and this segment D. Then the statement of the theorem is really that A times B equals C times D. That's a theorem that high school students used to learn. Did any of you learn it in high school? So earlier generations, all high school students would have learned this theorem. Okay? That if you take a circle and you cut it with 2 arbitrary lines, then the product of these two is equal to the product of these two. Now today we would say, well, that's in terms of measurements. That if you measure this with a ruler and you measure this with a ruler, you get 2 numbers. And this is multiplication of numbers. The right-hand side is the multiplication of the numbers here and here. But that's not the way the ancient Greeks thought. They thought of everything geometrically, so that this length times this length was not a number, it was a rectangle. Okay? So instead of writing A times B, they would have thought about the rectangle with sides A and B. You create a rectangle with sides A and B, and then over here you create another rectangle with sides C and D. And the meaning of the theorem is that the area of these 2 rectangles is the same. So another important thing that you find in Euclid is the emphasis on constructions. A lot of the propositions are not statements about theorems, but they're often statements about constructions. They're telling you how to construct things using a rule, using a straight edge and a compass. So the straight edge, by which I mean a ruler without the markings, just a straight edge, and a compass are the basic tools in Euclidean geometry. And Euclid wants to show us how to construct a lot of things with these. For example, how do you get a midpoint of a segment? You use a compass. You can't use a straight edge. You can't measure it and just sort of, divide the number in half. You put your compass with center here and arm here, and you swing a circle. And then you get the same compass, and you stick it center here, and you Put it here, and you make another circle. And these two circles intersect. And where they intersect are 2 points, and then we join those 2 points with our straight edge, and we've got our midpoint. In fact, we've got more. We've also created a perpendicular to the line. So we've been able to make a midpoint and perpendicular to a line. The same kind of idea allows Euclid to do one of the first things that he does, is to create an equilateral triangle. So he says there is an equilateral triangle on any side. You give me a side, I'll build you an equilateral triangle on that side. How do you build an equilateral triangle? You get your compass, center it here, arm here, swing it up. That's the same thing we just did there. Center here, swing it up, swing around. And now this point, instead of dropping a perpendicular, we're just going to connect. Is it clear that that's equilateral? Yes, because this is an arc of a circle, so that distance is the same as that distance. And this is an arc of a circle, so this distance is the same as this distance. So all these three are the same. Many years later, in the 19th century, people started looking at Euclid a little bit more critically. They started thinking, well, should we really believe all of this? And is it really logically tight? And they looked at this argument and they said, well, this is all well and good, but how do we know that these two circles intersect? After all, if I draw one circle through some point and I draw another circle through another point, maybe those two circles meet and maybe they don't. Don't we need to prove that these two circles actually meet to be able to get that point? Okay, so to Euclid, well, it probably was obvious because you can sort of just do it and you'll see that it works. But maybe there is a little bit of a logical problem there. Creating a square, that's pretty easy. I'll leave that to you to think about how you can create a square. And let's go to a much more interesting thing, the pentagon, or a regular pentagon. Regular pentagons are notoriously hard to construct just by drawing it on the board. If I do it like this, I invariably get something which doesn't look very regular. Okay? So how do you actually draw a regular pentagon? Well, Euclid gave it a construction, and Ptolemy also later on gave another construction. But I'm going to show you a construction which is goes to Redmond in the 19th century. Okay, much more modern construction. So here's a modern construction of a pentagon. We'll start with a circle. We'll start with any old diameter. And the first thing that we'll do is we'll draw a perpendicular to our diameter through the center. Okay, so step one is draw a perpendicular to the diameter. All right, let's call this O, let's call this A, B, let's call this C. Step two, find the midpoint of OC. How do we do that? Well, I've showed you how to construct a midpoint over there. So we can construct this midpoint, let's call it M. Now I'm going to join AM. And now I'm going to do something new, which I haven't yet explained how to do. I'm going to bisect these two lines. Bisect the angle. So I'm going to take that angle there, and I'm going to find an angle bisector so that this angle is the same as that angle. I'm going to do the same on the other side because angle bisectors come in two. So that's going to be the same as that. So bisect the angles, or the angle formed by the lines OC and AM. So let me show you how you bisect an angle. So there's some angle. How are we going to bisect it? We're going to take our compass and put it right here and make a circle. And then we're going to, well, we're going to keep the compass open at the same distance, so we can actually, we're going to center it here, and we're going to draw the circle through here. And then I'm going to go over here and do the same thing over here. It's centered here, through here. Now those two circles that I've just drawn intersect, well, they intersect here, but they also intersect at this point. And then I get my straight edge and I join that with our initial point, and those are the same. Now what about, there's actually another bisector over here. If I, instead of choosing these 2 points, if I had chosen this point and this point, by continuing this on, and done the same thing, I would have got a point over here. I would have gotten another bisector. It's actually always two bisectors. So that's how you bisect. And so we have these now, these bisectors. And suppose that they meet at D and E. Then the step 5. Draw perpendiculars to AB through D and E. There and there. That's perpendicular and that's perpendicular. And what do we get? We get this point, this point, this point, this point, this point, and that one forming, if I'd done it accurately, a regular pentagon. So 6 is connect the meets with the circle. Now, that's very nice. So you might say, well, what other regular polygons can you create with a ruler and compass? Can you create a hexagon? Yes, you can create a hexagon. That's easy. Because once you have an equilateral triangle, you can say, you can sort of just continue each one of these things out, and you get 6 points. How about a septagon with 7 sides? Also, by the way, sometimes called a heptagon. Seems to be a division between septagons and heptagon for the name of a 7-sided figure. Can we create a 7-sided figure with a ruler and compass? The answer is no. Can't be done. Eight sides is easy. An octagon That's easy. You just take a square and do some bisecting. 9 sides, a nonagon. Answer is no. So even if you take a 90 equilateral triangle with what we would say is 120 degrees, just dividing this into 3 equal pieces, that would be 40 degrees each. You can't do that with the ruler and compass. So when you take your protractor, you know, it has very nicely 90 there and 30 there and 60 there. 30 and 60 are fine. You can construct them. 45 is fine. You can construct that. But 20 degrees, you can't construct that. Doesn't matter how clever you are. Can't construct it with a ruler and compass. So in some sense, a protractor is a rather sophisticated technology, because there's this 20 sitting there, but how do you actually get that 20? How do we know it's there and not a little bit above or a little bit below? It's a little bit sophisticated. Angle measurement is actually quite problematic, and that's why Euclid's Elements avoids angle measurement. The 360-degree system that we use today goes back to the Babylonians. Euclid would certainly have been aware of it, but he did not use it. So Euclid knew it was problematic. Euclid avoided the Babylonian 360-degree system for angles. Okay, so what's the story here? Which polygons can you create and which can't you? Well, this was discovered by Gauss, great German mathematician, much later, beginning of the 19th century, when he was a teenager. And he discovered that an n-gon, a regular n-gon, is constructible precisely when you could write n as some power of 2 times some prime p1, prime p2, up to some prime pk. With the pi's distinct Fermat primes. What's a Fermat prime? It's a prime of the form 2 to the 2 to the, L plus 1. 2 to the 2 to the L. So what do these Fermat primes look like? If L is 0, then we're going to get P equals 2 to the 1, so that'd be 3. If L equals 1, then that's P equals 2 squared plus 1, that's 5. When L equals 2, that'd be 2 to the 4th plus 1, that's 17. When P equals 3, that's P 2 to the 8th. What's 2 to the 8th? 256. So add 1, 257. P equals 4. Okay, then it's some other number. I don't know what it is. They're all primes. But I think these are the only ones. The only ones known. So people have investigated which numbers of this form are prime, and they've, you know, you plug it into your computer and try to work it out. But I don't think they found any more than are on this short list. In particular, though, Gauss was very, he liked this result a lot. It means that the regular 17 gon is constructible by a ruler and compass. And constructions for the regular 17 gon were given in the 19th century. They're a little bit like the Richmond's construction, but a lot more elaborate. So Euclid's work was a great thing. And I have to mention sort of the culminating aspect of it, which may have been one of his motivations for doing the project. The Greeks were fascinated by objects like this, which are three-dimensional analogs of regular polygons. This is a dodecahedron. It's a regular polytope. Each side is a regular 5-gon. And there are 1, 2, and 5 here. There's 12 sides. And closely connected to it is the icosahedron, made out of 20 triangular faces. And these are 5 of the Platonic solids. So the high point of Euclid, which he finally gets to somewhere in book 13, I think, after he's done a lot of plane geometry, then he does some solid geometry in 3 dimensions. And the high point is the construction and the study of the 5 Platonic solids. Named after Plato. And the 5 Platonic solids are, the simplest one is the tetrahedron, which I can try to kind of draw a picture of. It's got a triangular base and then 1 point. And of course a cube. And an octahedron. Which you get by taking a square base and putting 1 point above and another point below. And joining them all up. So here we have 4 triangular sides. Here we have 6 square sides. Here we have 8 triangular sides. And then there's the dodecahedron and the icosahedron. So the dodecahedron has 12 pentagon sides, and the icosahedron has 20 triangular sides. And they proved, Euclid proves, that these are the only ones. These are the only regular polytopes consisting of faces which are all the same. All the faces look the same. All the faces are regular polygons themselves. They're the only regular solids. It's a little bit subtle because you can prove that there are only these 5, but you at some point have to actually show that this thing actually exists. Okay? So if you appreciate that it's a mathematical challenge to show that this exists, you're already sort of on the way to understanding some mathematics. Because you might say, well, isn't it obvious it exists? Here it is right here. But maybe it doesn't really exist, and maybe I've had to force the thing to fit when it really doesn't naturally fit. In other words, maybe one of these pentagons is not exactly a pure pentagon, but only 99% approximation of a pentagon, or 99.999%. How do I know that it's exactly, that these are exactly pentagonal faces and that they fit together exactly like this? There's a quite a nice construction system called Polydron with faces, solid faces that you can put together. If you play with this and you start making a dodecahedron, you'll notice that at some point it becomes rigid. At first it's floppy, and then you add enough faces it becomes rigid, and then there's just enough room for that final face. And it's kind of like a small miracle that that final face just fits on that hole that's left from the other ones. And that's the miracle that the ancient Greeks appreciated. They realized this is amazing. And so they actually had to construct them. Stillwell has a very nice diagram in his book showing a very elegant construction using a golden rectangle. Okay, the golden rectangle is another favorite object of the ancient Greeks. With sides 1 and tau. What is tau? Tau is 1 plus root 5 on 2, which is 1.6, I always forget, 1.61803398887, blah, blah, blah. It's a very important number in mathematics. Where does it come about? Well, it comes about in the pentagon. If you have a pentagon, one we constructed, and that has each side 1, then the diagonal, it's 5 diagonals, they're all the same. Each diagonal is tau. And what Pacioli discovered, who was a friend of Leonardo da Vinci's, according to Stillwell, is that this rectangle, made which has proportions of the golden rectangle, is naturally connected with this dodecahedron, not the dodecahedron, the icosahedron here. If you look at this in the right way, you see exactly 3 golden rectangles put together in a nice way. How can you see that? Well, let me just slip this in here. And you see that? So that those four vertices, these ones right here, they form a nice little golden rectangle. But also there's a golden rectangle in that direction with these 4 vertices. There are 12 vertices altogether. So that's one group of 4. That's another group of 4. There's one more group of 4 left over, which is that golden rectangle.
That pretty much goes for any 4 sort of corresponding vertices?
In this object? Well, I think, yes it does. So, we could also go diagonally like this too here. But the point is, if you just concentrate on these 3, then you have a situation where in the x, y, z plane, you can have one rectangle like this, one like this, one like this, and one like this. And you know what the coordinates of all the points are because they're all just made out of 1s and taus. And then you can check that you got lots of equilateral triangles using analytic geometry. Okay, so that's actually our problem 4, but it's a starred problem, meaning that it's only for the 3560 students. So problem 4, check Pacioli's construction. Okay, Stillwell's book has this as an exercise. It's 2.2.2 in Stillwell. All right, so that's a very quick introduction to Euclid's thinking. Very important, influential book that, well, just had so much influence on the course of civilization. So after a break, we're going to have a look at a few other aspects of Greek geometry.